Greetings, everyone. This is the last section of Chapter 6, Section 6.5. It's on average value. Remember, we skipped sections 6.3 and 6.4. Those are BC topic sections, and so those of you who come back to me for BC next year, we'll cover those. So, average value. The word average comes up a lot in mathematics, and it's every single time it does come up, it is related in some way to the other concepts, but you have to make sure you understand the context in which we are dealing with the word average. In this class, we've already dealt with average in the phrase average rate of change, and now we're going to be talking about the average value. I'm going to come back later and make a connection between the two because they are connected to each other, but for now I want to develop the idea of average value first, and then from once we have that understanding, we'll come back and connect it to what we already know. The main point, one main point that we have to come across in this is whenever you see the word average in mathematics, understand that you have to make sure you recognize the context in which it's being asked. Is it asking for the average value? Is it asking for the average rate of change? Or is it going back to the statistical notion of average, which again is related? Are we going to go back to that notion at some point? So let's get on with this here. Remember, if I have to find the if I have a collection of numbers, and let's say they're a bunch of numbers y1, y2, y3, ... y sub n, and they're just numbers, and I want to find the average of all these y sub i's. I want to find what the average number is. Then we would just, from 4th grade mathematics, to find the average, we would add together all of these y values. Add them all together like this, and then divide by how many there are. Divide by n. And that's how we find average. Back in, like I said, 4th or 5th grade, whenever you first learned it. But now, here, the phrase average value is going to be applied in a slightly different context. And so let's think about the context we're going to be dealing with here. The context is, let's suppose for a moment we have a graph that gives us, at some time t on the horizontal axis, the temperature, capital T, of some location. So let's say for a moment, let's talk about a place that's not California where things can go below zero a little bit. And so let's talk about something that looks like this. So that it started at some number above zero, went below zero for a while, came back above zero. How would we find the average temperature of this location, say, over a 24-hour time period? The problem with this is, and it's the difference between the example that we had up here versus what we're talking about now, where here we have a finite number of points, okay? We have n particular values that we're going to average together. Well, here the temperature takes on an infinite number of values because this is a continuous function. And so the issue is, how do we find the average temperature when we have an infinite number of different values with which to calculate and then try to give an average from? Obviously, we can't average an infinite number of things in the usual way of just adding them all together and then dividing by how many there are, because we cannot divide by infinity. Infinity is not a number. And so we're not even going to be able to divide or add an infinite number of things together in this way. So what are we to do? Well, as we talked about when we got into Chapter 6, I was trying to give you that overarching idea, the big concept behind how we handle things in calculus. When there is a quantity that we want to calculate that we don't know how to calculate, we try our best to approximate it some way. We try then to make the approximation better, and then we try to make the approximation exact by hopefully, or usually rather, taking a limit. And so that's the same idea as what we're going to try to do here. Since I have an infinite number of points on this for this temperature, I'm not going to be able to, like I said, add the infinity of points together. But what I can do is I can select a finite number of those temperatures, space them out, and then add all those together and average those. And then I can make those, and that would be an approximation to the temperature. Not necessarily a very good one. I could always make the approximation better by adding more points, by taking more time, more points along this continuous time. Some finite number of points, but more. And then once we represent that as a quantity, I can then make the approximation exact by taking the limit of the number of points to go to as the number of points goes to infinity, and hopefully that'll be able to give me the average value, or in this case, the average temperature. So we're going to use the same concept that we used back in trying to find the slopes of the tangent line, back in trying to find the area bounded by a curve. Excuse me, my phone's ringing. All right, so here's the problem that we're trying to address. Suppose we have a function y equals f of x, and we want to find the average value of y on the interval from a to b. Note, we're finding the average value that y takes on. Y is going to have a bunch of values. It's going to vary. We want its average value. We're not looking for the average rate of change. I'm not looking to measure right now how y is changing. We've done that. We should know how to do that. And we'll make a connection with what we're doing today with that concept, because they're not identical to each other, but they are related. But we want to figure out, of all the values that y takes on, what value could we assign to its average? That, it's got some above that, it's got some below that, and this seems to be the general middle value, if you will. Not the median. Average is some sort of a middle value, but it's not the same exactly as the middle value. But we're trying to figure out the average value that y takes on. And so let's start by dividing the interval AB into subintervals, okay? And we should know how to do that. Right now you should be shouting out or writing down what delta x is before I even say it. But remember, we calculate delta x by the difference, b minus a, divided by n. We're dividing into n equal subintervals. This is going to start to look familiar, okay? Now, once we have our n equal subintervals, we're going to choose c sub I, a c sub I, in each subinterval. Now, this is kind of like choosing the height of our rectangle as some point within each subinterval. It could be the left-hand endpoint, could be the right-hand endpoint, could be the midpoint, could be any other value in between. So we're choosing a c sub I just like we did back with that concept of, finding the height using our Riemann sums. Now, from this, we're going to calculate the value of y which is, of course, just f of c sub 1, f of c sub 2, ... We're going to run out of space, so let's just keep it like that. f of c sub I. Actually, I should probably put that as f of c sub n. That's the last one. Each one of them is an f of c sub I. So I'm going to calculate the y value at all these. Remember I said I'm going to choose a finite number of the y values. I'm going to then add them together, and average them, add them together, divide by n. Okay. So I'm going to take these values here, and we're going to take them, add them together, as I said a moment ago. So f of c sub 1 plus f of c sub 2 plus ... f of c sub n, and we're going to divide by n. Okay. So we just generated the average. And this would be an approximation to y, okay? Not a very good approximation to the average value of y. Not a very good approximation necessarily, depends how big n is. I mean, it could be really good, could be not so good. But, we'll make it better by choosing more and more n. All right, so we should know that since we have delta x is equal to b minus a divided by n, we could solve this for n and then plug that in for n over here. Okay? Why are we doing this? Well, because we're going to get this into a form that's recognizable, that we're going to be able to use some more of our calculus tools to evaluate. So Be patient with me. If you multiply both sides by n and divide both sides by delta x, you're going to find that n is equal to b minus a divided by delta x. And so we're going to substitute that back into that expression over there. So let me get a whole new page here. So I have f of c sub 1 plus f of c sub 2 plus dot 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 plus f of n divided by b minus a over delta x. Now, from our fraction manipulation, we should understand that dividing fractions means multiplying by the reciprocal. And so what we're going to be doing here is, when we multiply by the reciprocal of the denominator right here, multiply by the reciprocal of this expression, delta x is going to move up to the numerator, and b minus a is going to stay in the denominator. So an equivalent way of writing this is going to be 1 over b minus a. Even though it stays in the denominator, it's just a constant, so I'm going to factor it out. And then we're going to have f of c sub 1 plus f of c sub 2 plus dot 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 plus f of c sub n times delta x. Now we have a faster way of writing this, and so let's go ahead and do that. This is 1 over b minus a. This is just a summation right here, every term being multiplied by delta x. And so I can write this as the sum from I equals 1 to n f of c sub I times delta x. This look familiar? I hope it does from chapter 5. Now again, this is just an approximation to the average value of y. We make the approximation better by making n larger, and we said we'll make it exact by taking the limit. So the average value of y, or the average value of f, since f is also our function, the function that we're using, f average, is going to be the limit as n approaches infinity, 1 over b minus a times the sum from I equals 1 to n f of c sub I times delta x. Now this 1 over b minus a portion right over here, that's unaffected as n goes to infinity. That doesn't change. So that's just a constant. And by our constant multiple rule, we can actually move that in front of the limit. And I could say that f average is 1 over b minus a times the limit as n approaches infinity, the sum from I equals 1 to n, f of c sub I times delta x. Now, this limit right over here should look familiar. Okay, provided f is continuous, that limit exists. We say the function is integrable, and so f average can be written as an integral. What would be the integral? Well, this 1 over b minus a doesn't go anywhere. The integral is going to replace just the limit portion. And so we're going to get 1 over b minus a times the integral from a to b of f of x dx. And this is what you're going to want to memorize as your average value integral. Then that's it. If you have a continuous function f and you want to be able to find its average value on the interval from a to b, then you just got to take 1 over b minus a times the definite integral from a to b of the function itself, f of x dx. All right. So let's suppose for a moment that v of t is the velocity of some object. And we want to find the average velocity. A little sloppy there, but you know what I said. Find the average velocity of the object on the interval from a to b. Well, according to the average value integral that I just gave you a few moments ago, all I have to do is to figure out the velocity average here is go 1 over b minus a times the integral from a to b of v of t dt. And that would be it. Okay, now, because I didn't give you a particular velocity expression, some linear, quadratic, whatever, some function, there's nothing more that we really need to do right here, but I'm going to be connecting this now to that, to the idea that we talked about before of average rate of change. So average velocity is this. This is correct, okay? But if we recall way back in chapter 3, I believe, might have been in chapter 2, but I think it was in chapter 3, we said given the position function s of t, the average velocity, and we actually defined it this way, the average velocity on the interval from a to b was s of b minus s of a over b minus a. You may or may not recall that. If you don't recall that, please recall that, okay? In fact, this is a big concept that comes up on the AP exam quite a bit. They love to use motion problems, and if you don't know this relationship and can't connect this back to position and velocity, you're not going to do it as well as possible. But this is how we found average velocity. In one way, we analyzed this, that, let's say that the position function is measured in meters, and then so up here s of b minus s of a is in meters, and then the interval itself is measured in seconds, and we looked at something like this and we got meters per second as the units, and that is a velocity set of units. We also, this is our difference quotient. We took the limit of this to get the instantaneous velocity and still got meters per second. So this is something we did a long time ago, and hopefully you recall this relationship. But let's wait a second. I got average velocity using this technique right here, and it's a difference quotient. This is an average rate of change, but it's the average rate of change of the position function. And that's supposed to be the same thing as what we got over here. The average velocity was this integral. They are the same thing, whether or not you see it directly or not. If you think you see it, pause the video and try and work out the details. That would be a great practice for you. But if you don't see it, let's figure out what the connection actually is. Well, remember, to evaluate a definite integral, we use either the fundamental theorem or we called it also the evaluation theorem. And so we need to find an antiderivative of v of t. And so to work this out, we still got our 1 over b minus a here. And, well, what's the antiderivative of the velocity function? That's just the position function. And we don't need a plus c on this because we just need any antiderivative. And so it's s of t evaluated on the interval from a to b. And of course we evaluate this by plugging in b, plugging in a, and subtracting the results. And when we do this, we get the exact same thing that we just had on that previous page. We get the change in position over the change in time, which is what we defined average velocity to be way back in an earlier chapter. Completely consistent. Average value and average rate of change are linked together, but they're talking about two different functions. If I want the average velocity, it's either the rate of change of the position function, the average rate of change of the position function, or it's the average value integral. It's the average value integral given by our average value function. So there's a direct connection here, okay, that you can use in a couple different ways. Knowing that you want the average value of a function, you can just set up this integral for that function. See, the connection here is that this is v and this is v, okay? If I want the average velocity, the function that goes in that integrand is the velocity function itself. But if I want to use an average rate of change, then I have to use the antiderivative and then set up my average rate of change for the antiderivative to get the average value for that function. So you have a couple different ways to go about it, okay? We should probably do an example for a moment. And we'll do this a couple different ways, maybe. Let's let the a of t, which is equal to negative 3t plus 4, be the acceleration of an object. And let's find the average acceleration on the interval from, let's say, 2 to 7 units of time, whatever those happen to be. Pause the video and go try to work this out for yourself. So, hopefully you pause the video. And the average acceleration, which I'm just going to A with a little AVG after it here like this, is going to be 1 over B minus A, 1 over 7 minus 2 times the integral from 2 to 7 of the acceleration, which we said was negative 3t plus 4 dt. Let me double check that. Yeah. And so we can work this out by the evaluation theorem, 1/5. Antiderivative here would be negative 3 halves t squared plus 4t, evaluated from 2 to 7. And then we got 1/5. And then plug in 7, and we get 49 times negative 3 halves, and then plus 28. And then from that, we got to subtract what happens when we plug in 2. So we get, well, if I plug in 2, I get 4. 4 divided by 2 is 2, so we get a negative 6 plus 8, which is going to be easier to calculate than this negative 3 halves of 49. Still got that 1/5 floating around out here. Half of 49 is 20, what is that, 24 and a half? 24 and a half times 3 is going to be 73 and a half, and it's negative, and you got to add 28 to it. 73 minus 28 would be 41. I'm sorry, we get negative 45.5. And then minus, and this is going to be a 2 over here, so minus 2, or negative 47.5 over 5. And if you want to rewrite, whoops, I'm trying to scroll the screen. If you want to write that as a decimal, so 9.5, negative 9.5. So there's your average acceleration. Now, another way we could have obtained that, remember, is using the average rate of change of the antiderivative. So the average acceleration is going to be v of b minus v of a over b minus a. And since we had a of t as negative 3t plus 4, v of t would be negative 3 halves t squared plus 4t plus a constant. And we don't have any information with which to calculate that constant at the moment, but to get the average acceleration, we would take, the negative 3 halves, and we take 7, negative 3 halves of 7 squared plus 4 times 7 plus c. That's our v of b, rather. And then we do the same thing with, I'm just running out of space here, 2 squared plus 4 times 2 plus c, and we'd subtract all that, and then divide by 7 minus 2, which gives us the 5 that I accidentally wrote. But we're going to get, you could see we're going to get the same answer. The c's that we have here are going to subtract from each other, and we're left with the exact same result that we had on the previous page. So there was a couple different ways of going about generating that answer. Okay, so the last thing we need to talk about is a theorem in this section, and then we'll be done. And here's the theorem. It's called the mean value theorem for integrals. And this should make some sense because the word mean in mathematics is average. There's another word for average. And so this is like an average value theorem for integrals. It says if f is continuous on the closed interval ab, then there exists a number c in the closed interval ab such that f of c is equal to the average value of f, which of course is the integral, or 1 over b minus a times the integral from a to b of f of x dx. So write that down, pause if you need to. I want to write over this a little bit. Now if I take the expression here, ignoring the f average, and just take these two outside expressions, and I multiply both sides by b minus a, then the integral is by itself, and now I have f of c times b minus a, so I get this expression down here that is the definite integral from a to b of f of x dx is equal to f of c times b minus a. Let's interpret these things and make sure that we understand exactly what it's telling us here. So remember, depending on depending on the properties of f, this here, if f is non-negative, is the area under the curve. So this is area under f. Well, what's this over here on this side? Well, this is the width of the integral b minus a times some y value. This is just the area of a rectangle. And so what this is telling us, this relationship, this mean value theorem for integrals is telling us is that the area under the curve of f between a and b is going to be equal to the area of some rectangle. But we know now exactly what the height of that rectangle has to be for this equation to be true. The height of the rectangle is going to be the average value. The height of the rectangle is going to be the average value. Just repeating that for emphasis. Here's a picture. It's in your book. It's not the greatest photo that I took right now, but it's illustrating the point. So we have our function f, which is, this function out over here, and the integral is just the area bounded by the curve. The rectangle here that we have gives us the exact same area as the area bounded by the curve, and here's the relationship that's a little bit blurry, but that's the important part. The height of the rectangle is the average value. This is a conceptual understanding of what that average value represents. It's the height of the rectangle needed in order to have the area of the rectangle equal to the area bounded by the curve, or the net signed area. Substitute that phrase in place of area and their equivalent. If you look here, it may be a little bit hard to tell, but I think with some imagination, all of this area that's excluded from the rectangle is going to be exactly the same as this area that's included in the rectangle, but that wasn't included in the area bounded by the curve. This is a little taller here, and this is not quite so tall, but it's wider. And so, we're just reshaping and redistributing the area so that this area that was left off by the rectangle is filling in the extra space that was taken up by the rectangle that shouldn't have been included or wasn't included with the area bounded by the curve. And there you go. That's the end of chapter 6. So, watch this again if you need, or watch some parts of it again. The average value does come up quite a bit on the AP exam, so memorize that integral. Remember, when you see the phrase average or the word average, how is it being used? Are they talking about the average value, the average output? Are they talking about the average rate of change? Because those two concepts are related, but they're not exactly the same thing. Go study.